Hi, I'm Bill Cammuso. I'm happy to talk to you today about homogeneous charge compression ignition, or HCCI engines, some of the limitations on their operations and efforts to overcome those limitations. The idea with an HCCI engine is to combine the compression-initiated combustion of a diesel engine with the premixed fuel and air charge of a spark ignition engine. The watershed work in this field was identified with Onishi and team in 1979, who were looking at two-stroke engines and the possibility of this offered in their research realm. That body of knowledge was subsequently expanded into four-stroke engines, into the effect of equivalence ratio and residual gases, and to a much deeper understanding of what actually happens inside the cylinder, and continues to this day with opportunities to expand the applicability of these engines to real-world applications. The idea with the HCCI engine is just as described. Unlike a spark ignition engine with a turbulent flame propagating from the spark plug, or a conventional diesel engine with a diffusive flame propagating from the injection of the fuel, all of the fuel and air premix in an HCCI engine and initiated by compression. So combustion theoretically is spatially uniform. As such, there is no flame propagation, but the combustion event occurs in the cylinder as fast as the reaction mechanism will allow at all points uniformly. Why do we do this? Well, it has a lot of potential. Combining the high compression ratio of a diesel engine's lack of throttling losses because we can control engine speed through the equivalence ratio and the introduction of fuel into the premix charge. Also thermal efficiency due to the low temperature combustion arising from the lean operation that we'll talk about more in a moment. There's a smaller thermal gradient between the combustion chamber and the surroundings, and hence reduced heat losses. Moreover, it has the prospect of greatly reduced emissions in terms of oxides of nitrogen and particulate matter, about which we'll go into subsequently as well. As expected, the profile of heat release in an HCCI engine is extremely rapid. As the leftmost peaks in this panel show, those are the HCCI peaks. Very rapid heat release rate and hence pressure rate rise within the cylinder as compared with the bell curve to the right, which is that of a typical spark ignition engine, which is much more moderate and much more prolonged as the crankshaft goes through its motions. There's a lot going on in this graph, but it tells us a lot. These were experiments comparing the effects of exhaust gas recirculation and equivalence ratio, the latter of which is on the vertical axis. If we focus on that, we see the operating window in the unhatched area really being a sweet spot well below that of the typical stoichiometric equivalence ratio. What has been found is HCCI engines have a lower operating limit defined by unstable combustion and misfire, and an upper operating limit defined by knock. There is a propensity for knock in this environment at very low levels of engine speed and load, typically about 40% that of a spark ignition engine. So as shown in this graph, again looking at the vertical axis, we're required to keep the equivalence ratio low in order to prevent knock and allow the engine to operate. That results in the lower combustion temperature, typically 1500 Kelvin or less. And also shown on this is an effect that will be discussed subsequently, that of the effect of exhaust gas recirculation. These are very high ratios shown here, anywhere from 13 to 32% compared to 5 to 15% in an SI engine, necessary to help moderate that spike of heat release through the introduction of high heat capacity gases and displacing oxygen in the combustion charge. The attraction on the emission side with oxides of nitrogen and with soot. So this graph is a bit stylized. What the researchers were looking at in particular that they call the desirable path, pertained to conventional compression ignition engines. And you can see a very narrow margin of error between the equivalence ratio and combustion temperatures that could result in either oxides of nitrogen or soot emissions. At the lower left, that rectangle of HCCI's operations, typically at 1500 Kelvin or below, an equivalence ratio well under 1 throughout its operating range, put it well out of danger of forming appreciable amounts of either particulate matter or NOx. And this is one of the key attractions in terms of the sustainability profile of the HCCI engine. However, there is a trade-off on the emissions front. This graph shows that there can be a propensity for greater unburned hydrocarbon and carbon monoxide emissions under HCCI compared with its more established counterparts. At equivalence ratios here below about 0.2, we can see a great increase in the emissions of carbon monoxide. What we're talking about here is lower combustion temperatures, which have crevice effects and boundary layer effects, and at lower and lower equivalence ratios, a cold core effect, which results in incomplete combustion or oxidation of CO into CO2. And at still lower equivalence ratios, we see, due to the same effects, incomplete combustion of hydrocarbons into CO. So at very low equivalence ratios, we're seeing an increase in unburned hydrocarbon emissions. This effectively sets a floor on the equivalence ratio that can be used in HCCI unless some other mitigating mechanism is employed, such as catalytic aftertreatment. Now remember, we're talking about lower combustion temperatures, which can have an effect on the suitability or availability of catalytic aftertreatment to be functional, which normally requires a fairly elevated temperature to be successful. So this defines an operating range for HCCI. We have a lower operating limit limited by instability of combustion and misfire, as there isn't enough fuel to combust at very low equivalence ratios, and potentially high unburned hydrocarbon and carbon monoxide emissions. This, by and large, can be managed, but it's the upper operating limit that poses the biggest challenge. As we get into the propensity for engine knock and an indicated mean effective pressure of roughly 5 bars in unaltered form in HCCI versus 12 bars in a spark ignition engine and 18 bars in a diesel engine. This really would be nothing more than a technological curiosity unless we can broaden that operating envelope. So what are the efforts to do this? One proposal that's been identified or possibility is the use of fuels that are specifically tailored to combust in multiple steps and hence broaden the heat release and pressure rate rise within the cylinder. In this example, PRF 80 is found to have this profile called low temperature heat release, where there is some heat released from 340 to 350 degree crank angle in advance of the high temperature heat release up here around 367 degrees. Isooctane, by comparison, is absent that and isn't really able to be utilized in such a manner. But specifically tailored fuels can be found and engineered to help broaden and flatten the heat release within the HCCI combustion chamber. Fuel composition. Similarly, these researchers explored blends of gasoline and ethanol and found that different blends of ethanol could be used to operate within, this is a rather simplistic graph, but engine load of up to 70%, but not down in this case of this particular blend of 2.5% ethanol, below 40% engine load. Other blends, 5%, 7.5%, can handle a lower engine load, but not the higher one. So there's no particular blend with ethanol that dominates across the entire operating range. It does open the possibility for a dynamic blending of fuel to be able to expand the operating range. But again, in this particular case, nothing higher than a 70% load as defined by the researchers, and hence not approaching that of a typical SI or CI engine. Partial fuel stratification refers to a bit of a deviation from the pure HCCI concept and involves the direct injection of a metered amount of fuel into the combustion chamber after the initial charge. During the combustion process, the vaporization of this liquid fuel injected into the cylinder can help absorb some of that heat of combustion prior to combusting itself, and hence moderating the pressure and heat release profile within the temperature, which we see as we move from the yellow to the black line in these experiments shown here. Thermal stratification is another option, which combined with the prior fuel stratification is really approaching commercialization. The idea with thermal stratification is again to deviate from the pure HCCI concept, keep the engine defined or built such that it will not exceed the auto ignition threshold unless prompted through a spark, through a glow plug, through a pulsed flame jet, some mechanism to create the conditions that are right for auto ignition. Examples here, two-stage combustion is described, are a special spark plug with a pre-chamber where spatially localized ignition is created, or in the bottom panel, a piston which at top dead center defines a small area for initial combustion, which then propagates to the entire cylinder as the piston moves downward. The idea with this then is to leave the pure HCCI mode and deliberately initiate combustion at more moderate levels of engine speed and load. These researchers were able to get 7.5 bars rather than 3.5 using spark-assisted compression ignition. However, that doesn't get us again to the full operating range of, say, 12 bars. And what they propose is transitioning to full spark ignition at higher engine speeds and loads, which is in fact something that Mazda is very close to doing, has attempted to introduce into the market. The popular press reports that has not been commercially successful due to some factors that may be other than technological. But this is an incorporation of HCCI into a portion of the engine's operating range. Forced induction. Well, one way to increase cylinder pressures is through supercharging. What's been found here is there are rather stringent limits on that due to the fuel octane number, whereas isooctane, which has the lowest octane number of this sampling, could produce higher IMEPs in the top panel. Under boost, it could not. So there are some limits based on the fuel octane number to what can be done with forced ignition. Dilutants. So EGR we touched on is really necessary to help retard the profile of combustion in the cylinder through heat capacity being able of the charge in the EGR being able to carry away heat and displacing oxygen in the intake charge. Water injection is a similar approach to that that's been used in spark ignition engines. We don't have the benefit of color in this chart, but as we move from upper left to lower right, suffice it to say that increased levels of water mist in the intake charge have been found to help moderate the heat rate production within the cylinder. Thus, the onset of knock at higher engine speeds and loads do limit the applicability of HCCI to the real world. Enhancements such as fuel and thermal stratification, some limited amount of forced induction, and dilutants can certainly help with this, but none of these gets us all the way there to the levels of SI or CI engines. But further research may change this.